All right, in this last clip of our very short first section of chapter 16, I just wanted to point out that the gradient of a scalar valued function is a vector field that you've been familiar with for a long time. So we didn't talk about it at such a course because we hadn't really gotten into vector fields, but yeah. So suppose we take this function here, f, it's a function of two variables, and the output is just a scalar, right? Then the gradient of such a function is naturally going to be a vector field. So we've got its partial derivative with respect to x and its partial derivative with respect to y, exactly the same number of variables as went in the first place. So it's going to be a function from R2 to R2, and that's the definition of a vector field. Now, I've drawn this particular example over here. It's actually sort of a famous example. It's called a monkey saddle. Can you see why? So it's like a saddle where, you know, you've got like monkey leg coming this way, and you've got monkey leg going that way, and then you've got like tail coming off down this way. Okay, that's a pretty bad monkey butt, but you get the idea, right? So I've also got sketched over here the gradient vector field. That's all the arrows, and the corresponding contour map. And so just for fun, you could doodle some of the flow lines on here so they would come this way and then go that direction, or maybe here and then come up here. You could also come in this way and then curve up, something like that. And those correspond to, here, let me get rid of the monkey butt. Let's see, roughly speaking, let's see, so the first one kind of came, so if you were, now keep in mind the gradient itself lives in the plane. It's down in R2. It's not up on the graph like I'm about to draw these curves. But if you were to trace along and say like, hey, what was the value of the function doing as we follow this flow line through the gradient here? Let's see, so it would be kind of like coming up this way and then going up. And you notice, see, it's like trying to climb that hill as steeply as possible because that's what the gradient do, right? You come in here, and then at any moment in time, these little paths are trying to, they're doing a greedy algorithm to get up the hill as fast as possible, which doesn't mean that they're doing the globally most effective thing. I mean, the globally most effective thing for getting up the hill as fast as possible would have been to just go like straight up there. But the gradient is local. It only sees what happens in a neighborhood. Anyway, so this is one kind of a gradient field, but it's a very important thing that not all vector fields are gradient fields. And it turns out actually that the question of whether or not a vector field is the gradient of something, this has lots of implications, and we'll talk a bunch more about it later in the section. So for now, I just wanted to introduce the terminology. We say that f is a conservative vector field. If and only if f is the gradient of something. And then in such a case, we say that little f is the potential. Okay, I guess the potential for f. It's everything that f could be if it grew up. No, just kidding. And then as sort of a last note, just by way of terminology, it's common to refer to the components of a vector field by simple names. And these are usually m, n, and p, or else p, q, and r. Our book goes with p, q, and r. So they would call this the p component and this the q component, and we're only in R2, so there is no r component. But so this would be, so we'd say p is 2xy, and q is x squared minus 3y squared. And sometimes they'll use the physics notation and write this as like gradient of f is 2xy I hat plus x squared minus 3y squared. J hat, this is neither here nor there. I'm just showing you some notation so that if I start talking about pi plus qj, you won't be totally freaked out by it. We'll see more of this later on in the chapter as well.